Hello, Marchik. How's everything going? My wife's going to hospital tomorrow to deliver our baby, so I won't be available in the next few days. So I thought I'd do a short video on my thoughts on the Cheshire experiment. It's a little bit easier because I can draw diagrams. So let me start off by writing down the initial state of the pointer in the coordinate basis, and the final state of the pointer. So this is all in our paper. Oops, sorry, that should be O. This is the weak value. So this tells us that when the weak value is real and non-zero, the state of the pointer shifts in the coordinate basis by an amount which is proportional to the weak value. So let's consider two scenarios. One when the weak value is real and equal to 0, and one when the weak value is imaginary. So these are the two cases we considered in our paper. So let me remind you what these sigma operators are. They are polarization detectors. Actually, let me write them down explicitly. So sigma A is equal to L here stands for left polarization, and R stands for right polarization, and A is a photon state occupied in arm A, and similarly for sigma B. So in the Cheshire experiment, these operators or pointers correspond to deflection of the beam. So let me draw the initial state of the beam like this in the coordinate basis. Okay, so this is the probability of detection, or the wave function. So when the weak value is equal to 0, there is no shift in the wave function, and so the probability distribution still looks the same, except for this not important scaling factor. So we can say, since the expected value is equal to 0 and the probability distribution has not changed, we can say that this corresponds to no polarization detected, as Aronov does in the original Cheshire paper. But what happens when the weak value is imaginary? When it's imaginary, the wave function no longer is a simple shift in the coordinate basis. So, so what does it look like? Well, okay. So first, let me remind that the measured value in the weak value is this real component. So we want the measured value to equal to 0. And in the Cheshire experiment, the way that Aronov explains that is that these polarization detectors are optical elements which deflect the beam left or right according to its polarization. So a good guess as to what the probability distribution of the beam looks like after its interaction with these detectors could look something like this. So here the expected value or detected weak value is equal to 0, and it has peaks at -1 and 1, which corresponds to deflection to the left and to the right. So what sort of state would produce this? Well, a linear state. So if we write down the linear state, we see that it's a equal combination of left polarization and right polarization. So when you have one of these detectors on this state, you would get this probability distribution. So what we have done is we've distinguished a no polarization from a linear polarization by the fact that no polarization corresponds to 0, and a linear polarization corresponds to an imaginary component with a 0 real component. Something else I probably want to quickly mention is if we have a general weak value which has an imaginary component, then we know that the final momentum state of the pointer is equal to its initial momentum state plus a value which is proportional to the imaginary component, and var p is the variance of the initial momentum. So what this tells us is that the momentum changes, which suggests that the initial wave function, which looks like this, should change after interaction with the pointer if there's an imaginary component. So these are my thoughts. I think a lot of the criticism from the referee refers to our interpretation of the Cheshire experiment, but I believe our interpretation is wrong. After rereading the paper, maybe there were some things which we could have explained more clearly, but I think I can write this up in a bit more formal sense, but I thought I'd give you my thoughts at the moment.